that's okay. Yeah. Yeah, record.
Sorry.
Ready to go?
Right.
Yeah, thank you. And welcome to our very first, this is our first hybrid. Second hybrid.
First hybrid, yeah.
First hybrid
Yeah.
session of the CDAR risk seminar. So thank you to everybody, Tudor and Sang and everybody who's been working to set this up. I hope we're going to be this way forever. Okay, today we are delighted to welcome CDAR postdoc Hubeyb Gurdogan talking about bias reduction in optimized portfolios through multiple anchor point shrinkage. That's MAPS.
Yeah. Yeah.
Over to you.
Yeah, thank you for the introduction, and thank you everyone for joining in physically and through virtual environment. And so this is an ongoing work with Dr. Alec Kercheval and Dr. Lisa Goldberg. This is a work in progress, and this is concentrating on the situation that in our optimization scheme we are considering more than one constraint as opposed to the usage area of other optimizers that was recently published, which is global positioning system, GPS, that is due to Dr. Alex Shkolnik and Dr. Goldberg and Dr. Papanicolaou. Okay, so let's get straight to the portfolio selection mechanism that we're going to use to analyze. Okay, how do I actually go to the next one? It just doesn't react. You're using the cursors. Okay, yeah, great. Okay, so all right, an optimized portfolio with a constraint set capital C, which is a P by K matrix holding the constraints on its columns, is defined as a solution to this quadratic program that is minimizing the variance against these constraints while trying to match with the constraints. So this is a general problem. The special cases are you can actually just have one column constraint, which is a fully invested constraint that is going to produce a minimum variance portfolio. Or if you actually have two columns in your constraint matrix, for example, the fully invested constraint, which is column of all ones. And also, if you put the second column as an expected return vector divided by the return target, then that will generate you an efficient frontier given that you have the true expected return vector. So, but in practice, we don't get we are unable to get the actual true optimized portfolio. Instead, we have an estimated portfolio that is solving the same quadratic program when you just replace the capital sigma, the covariance factors, with an estimation of that covariance factors. So changing the covariance matrix with its estimation is going to produce an estimated optimized portfolio. So, and I'm going to quote some words of Harry Markowitz, who introduced the Evie Rule, this quadratic optimization schemes. So in this quote, he says, in order to get a good estimate of covariance matrix, we should use statistical techniques. And also, he also speaks about the estimate of the expected returns as well, but they're more concentrated on the estimation of the covariance matrix in this work. So he says we should use the statistical measures to come up with an initial estimation, and then we should work on the entries of the covariance matrix through domain knowledge. So this is hinting the fact that many other estimators in this area of research that is starting with a priori and then just taking that priori, just shrinking that priori towards a target point that is determined by the domain knowledge. So that is what we will do on the settings of more than one constraint. So our research agenda is we first want to understand how the sampling error distorts the estimated covariance matrix, and in result it distorts the optimized portfolio weights. We wanted to understand the dynamics and how it is happening. We like to mitigate the distortion at an extent possible. At the end of the day, I like to draw a parallel to efficient frontier portfolios. So that is our research agenda, and then our findings are, so in this particular problem that we have multiple constraints, we show that each constraint added to the optimization scheme is introducing a remote optimization bias term of the leading eigenvector of the sample covariance matrix. So each constraint generates its own trouble that needs to be fixed. So regardless of the number of constraints, the multiple anchor point shrinkage is able to eliminate all the optimization biases at once in one shot. That is extending the usage of GPS method that is working on the single constraint optimization. So, by the way, I didn't mention, if you have questions, I'm free to be interrupted. So
you're taking the
yeah.
constraint decisions in the context of estimated means that you so this would also be uncertain, but you're not attempting to.
yes, good
Could you
point.
repeat the question, because I think the audience is
Yeah.
listening remotely.
Yeah, so he is asking the particular constraint type, the expected returns, and he is saying you're not. He's asking if I'm attempting to deal with the expectation of the returns. No, I'm not attempting to deal with those. I'm just taking it as it is given and just looking at the perspective of how it is distorting the variance of the portfolio. Yeah.
I just want to add, constraints come in maybe two flavors. Some are many where you actually know exactly what the gradient should be, and then ones like expected returns, where you might have to pick that estimate. So
Yeah.
obviously that's the top.
No, I understand.
Yeah, so the manager comes in and provides you an expected returns vector, and then definitely knows something about the market, but not the whole. So we're not attempting to fix the expected returns. We're just trying to understand how each constraint is adding to the distortion in the portfolio weights in terms of variance of the volatility of the portfolio. In other words, we're not looking at something like Sharpe ratio or not. We're not considering the Sharpe ratio. Okay, so all right, let's get started with how we measure the errors of the portfolios. So one measure we use is variance forecast ratio. That is basically the ratio of the true variance of your portfolio, that is the top of the fraction, and the estimated variance of the portfolio, that is bottom of the fraction. So we just calculate the estimated variance of the portfolio by using the estimated covariance matrix. So this fraction ideally should be 1, but we will see that it is a lot bigger than 1 if we go with the sample estimators. So, and the optimization having more than one constraint can also amplify the effect. Okay, so we are following a one-factor model of returns, where R here is a p by 1 vector, and beta is a p by 1 vector, capital C is a p by 1 vector. So beta is standing for, we can think of beta as an exposure to the market return, and we can think of capital X as a market return, and capital Z as the residuals. So under some standard assumptions, we have a rank 1 covariance matrix structure, where the sigma square is the variance of the capital X, and delta square is the variance of each entry of that residual. So we're assuming that each one of them are equal to delta square. Right, this is rank 1 covariance matrix structure we have. And how do we estimate this covariance matrix? So if you actually look at our estimator, capital sigma hat, so we are using n observations and p returns to come up with capital sigma hat. And so this is following the same structure of the rank 1 covariance matrix of the rank one covariance structure of the true covariance matrix. So this is only replacing sigma by sigma hat, beta by beta hat, and delta by delta hat. And if we set sigma hat times beta hat to SP squared minus alpha squared to the 1 half times h, and delta hat to that other constant, that is finishing the set of the family of estimates that we consider. Let's talk a little bit about what these constants are. H is standing for the leading eigenvector of the sample covariance matrix, and SP squared is standing for the leading eigenvalue of the sample covariance matrix. And go ahead.
Before you hear about notation, the IP. First
LP,
line, yeah,
how would you?
first line, shouldn't that be like an identity matrix? Second line.
Yeah, I'm suffering from LaTeX here. Maybe I should.
Yeah,
yeah.
so I think you want to just explain what the difference
Yeah,
in
yeah.
those symbols is, and
Yeah,
maybe
yeah, yeah.
revise the slides so
Yeah.
that it's more visually.
Good catch, Lisa. So IP is, yes, you're right, definitely. IP is a p-dimensional identity matrix over here. And LP is definitely different than that. LP is the average of the remaining eigenvalues. So you just take the list of eigenvalues of the sample covariance matrix, you take off the leading eigenvalue, and then you average the remaining eigenvalues. That is LP squared. Okay, so what? All right, then if you look at these quantities, delta hat is as p goes to infinity, is catching up to delta. It's a consistent estimate of delta, but not same here. So we will have some sampling error associated with the leading eigenvalue of S that will distort the constant overview of SP squared minus alpha squared in terms of its estimation performance. But in GPS framework, we see that the error in the leading eigenvalue is not really transmitting into the distortion of the minimum variance portfolio weights. And we are observing same here, even though we have more than one constraint. So we'll not worry about the sampling error in the leading eigenvalue. So we will be more worried about the error that we are making when we are coming up with an estimator of the leading eigenvector of the actual covariance matrix, which is H. So we have freedom. So from now on, we have freedom on our choice of H. So initially, we can set it to the leading eigenvector of S. That will be our priority. But at the end, we will be shrinking that towards some meaningful target points to get a better estimate of H. That is all it matters. We have to get a good estimate of little b, that is the beta over the norm of beta, so normalized version of beta. Okay, so let's go to, go ahead.
So I want to be clear about what the last paragraph says.
Yeah.
So I agree that GPS framework focuses on the leading eigenvector. Is this saying that errors in the leading eigenvalue don't affect the estimated minimum variance portfolio? Because they certainly do affect the projected volatility of the portfolio. The eigenvalues translate directly into projected volatility. Right? Is what I'm saying, it's does affect the position.
I'm saying that it doesn't affect the variance too much. So when you look at the asymptotic region, yeah, yes. All right. So let me reiterate. Tell the question out loud here. So we are. Dr. Anderson is asking. Is asking if the leading eigenvalue, errors in the leading eigenvalue, if it is not affecting the composition of the minimum variance portfolio, or is it not affecting the volatility of the minimum variance portfolio? Is that the right question?
I'm talking about the projected volatility. Any portfolio. The eigenvalue wrong affect your projected volatility.
What do you, how do you define projected volatility?
It's in the previous slide.
Do you mean the variance forecast ratio?
It's the denominator.
Okay, yeah, the estimated one. Yes. Yeah, estimated volatility.
Yeah.
Yeah. Yeah, so yeah, okay. I got your question. Yeah, so I'm talking about the true volatility. True volatility. So
That's certainly true.
second, please.
That's certainly true.
Yeah, go ahead, please.
Out here, so this comment, whatever it means, is true in a very specific setting. Not all settings have this property, but if you work in what I like to call the HL regime, where you have observations HI going to infinity, and L, which is the number of it's the number of securities, H going to infinity, and the number of observations, L, staying fixed. Then if you look at a formula for this forecast variance ratio, for example, asymptotically, the estimated eigenvalue drops out. So its influence is negligible and diminishing for large P, and this is proved in various places. Now, if you have other settings where, say, P and N get large together, this may not happen. So it's an asymptotic result. This ratio that
yeah, so okay, yeah, I should have mentioned this. Yeah, this is really GPS framework is also working in HL regime that I'm gonna now explain what it is. So these results are all in HL regime where number of observations are exceeded by the number of returns. Okay, so yeah, so we have N is standing for the number of observations, basically exceeded by the number of returns. And in order to approximate the conclusions of HL regime, what we do is we are setting N fixed and we are sending P to infinity. So this is the reasoning behind the asymptotic analysis that we do. Okay, and so here we define the optimization bias term. So let ZI is standing for the normalization of each constraint that is living in the columns of capital C. And for each ZI, we can define an optimization bias term of the leading eigenvector H. That is, so it is defined as the I optimization bias term, the inner product between VZI minus HCI times HP divided by 1 minus HCI squared. So where B is the normalized version of beta. Okay, so and one quick theorem about this is under the HL regime and under the modeling assumptions that we have, if the inner product between B and ZI is not converging to 0 as P goes to infinity. If it is staying away from 0, that means if you just think B as the north pole of the sphere, if ZI is staying away from the equator as P grows, then the limit as P goes to infinity of the optimization bias stays away from 0. So it is a finite non-zero quantity, almost sure. Okay. All right, so now if we go back to the definition of the optimization bias term, which I can write over here. By 1 minus HCI squared. If we actually set H equals B over here, so this inner product between H and B will be set to 1. And so this will be BZI and it will cancel out. So it will vanish the top of the numerator of the optimization bias term. And so that means if B were consistently be estimated, then the optimization bias terms will vanish at once. But that is forbidden by the HL regime. So we have low sample, so our sample estimator is not gonna get the B ever. So we don't have a consistent estimator because of the HL regime. All right, so that said, we can say the optimization bias terms are actually transforming the sampling error in eigenvalue estimation to the portfolio distortion. So I can illustrate that with this equation over here. So variance forecast ratio can be written as P times latest sum of the optimization bias terms squared plus finite asymptotic quantity where xi's are asymptotically finite as well. So this is the equation that governs the variance forecast ratio. If you see here, we have a P over here that results in an explosion of the variance forecast ratio. If these are all finite, and one other thing is there's a possibility that this optimization bias mass can clear itself with cancellations. We have more than one term here. We can have a cancellation over here, but we will look at that possibility later. For now, let's assume that each one has a contribution, and if that is the case, a possible solution is to actually kill all of these optimization bias terms at once. So whether or not if we have a cancellation of that optimization bias mass, killing all the optimization bias terms will remedy the situation blindly. Okay, so let's look at the spherical law of cosines. Okay, so the spherical law of cosines will actually invoke this equation where the optimization bias can be written as this fraction times cosine theta I square, where theta I is the angle between the geodesic connecting H and B and geodesic connecting H and Z. That is the angle. If that angle were like 90 degrees, then we would be ending up with cosine theta I being 0. So we wouldn't have any optimization bias. So okay, and from there, the remedy is the oracle estimator that will actually kill all these optimization bias terms by setting up those angles to 90 degrees is projection of B, the spherical orthogonal projection of B onto the subspace generated by ZIs and H. So that will, by the virtue of the orthogonal projection, spherical orthogonal projection, will actually set all those angles to 90 degrees. So if I were doing this on the RP, not on the sphere, but the RP, if I were just projecting onto the linear subspace, but not normalizing back to the sphere, that would be true by Hilbert projection theorem. So I would directly get all the angles 90 degrees when I connect B and the projection and the ZIs. So, but same thing is happening in the spherical geometry as well when you just project, when you normalize back to the sphere. So, okay, that means all of the optimization bias terms are set to 0 by the oracle maps estimator, that what we call is oracle maps estimator HL. So, okay, this is an oracle estimator because what we do is we are just projecting B, an unknown thing, to the subspace L. So if you don't know B, then how would you know the projection? So that is a question, and we just come up with a data-driven multi-anchor point shrinkage estimator that is converging to this oracle estimator in the asymptotic regime. And since this is converging to the oracle estimator in the asymptotic regime, the optimization bias term also converges to 0 almost surely. It's not setting it to 0 at P, but when you just grow P to the infinity, it's going to capture 0. And the important thing is it's just killing all of them in once. Okay, so this is the first part of the story. So we have like more than one source of the optimization bias and how to treat them. We just shrink H towards the all these constraints, and then that will just that will actually, if you do that optimally, that will kill all of the optimization bias terms. That is the first part of the story. Then let's go back to the question that I asked earlier. can the optimization bias mask that we just defined over there, that weighted sum of the optimization bias, can ever cancel each other naturally? Can we have that happy moment that the optimization bias terms kill itself? So, okay, we just look at, we analyze for k equals 2 when we have two constraints. So optimization bias mask converges to that constant capital A times dy1 plus y2 almost surely, where A is a strictly positive quantity and D is the ratio of the norms of the constraints, and y1 and y2 are a function of the normalized version of those constraints and B. So we have like separate two entities. One, the norm of the constraint, and the other is the normalized version of the constraint. So they don't actually communicate with each other. All right. So if you actually solve that linear part, we can have a happy moment if the ratio of the norms is equal to the ratio of y1 and y2, negative y1 and y2, and y1 and y2 are just functions of zi's and b. Okay, so what this really means? Let's illustrate this further. So let's look at the efficient frontier portfolios when we set C1 to the vector of all ones and C2 to gamma over RT. RT is the return target and gamma is an expected returns vector. Okay, so then if we actually take one step further in that equation when we were describing that happy moment. So notice that we have this freedom over the return target, which is we can play with the norm of this constraint that is actually generating the efficient frontier curve, right? So we're like looking at the efficient frontier curve at once here. So and we will have the optimization bias mask clearing itself if the return target is equal to the RT0 that I call the return target 0, which is the limit of the average of the squared returns times that quantity y1 over y2. So we have a single magical return target that is setting the optimization bias to 0, which is not the happiest moment. So because on the efficient frontier curve, we have a single return target that is making the optimization bias 0. That is not a big thing. We have lots of other portfolios, lots of other return targets that we can end up in trouble. So okay, let's take a look at the scenario that we have this situation that the optimization bias mask is clearing itself, and we are using the GPS method, MAPS method, and no method at all. So PCA method is the best here because it's already clearing itself at the PCA in that scenario. And MAPS method is attacking both of these optimization bias terms and killing them in the asymptotic regime, which will also set it to 0 in the asymptotic regime. It's going to be capturing the PCA performance. If you use the single constraint shrinkage, that is the GPS shrinkage, it will just attack the first one. It will just banish this one, and it will distort the other one. It will just wreck the natural cancellation effect of the bias mask. So it will just reintroduce the bias over here by killing one and distorting the other. So GPS method, if you use it in this context, it is actually going to, in this scenario, it's going to actually distort the already happy moment. So, okay, that is that. And then I have, under some restrictive assumptions, we have a theorem here. So if your expected return is following the structure, when you have a risk-free return times the vector of all ones, market return times beta plus some residual where we are imposing a structure to the residual. We want it to be orthogonal to beta and the vector of all ones. And we assume further that the market return is positive. In that case, that RT0, that is associated with the pathy return target has to be less than the RF, the risk-free return. That is telling us that we don't have a really practical happy moment in this case. All right, so go ahead, please.
Okay, our returns are determined by getting rid of optimization biases. Return targets are gotten by analysts who think they know what the return target is.
Yes.
So we can't just go, I mean, it may be that in some optimization, there's a good vector to put, but it may not be the right return target from
Yeah.
analysis.
Yeah, this is very restrictive. So we are just looking at the scenario that so your manager comes with a this is really hypothetical. Your manager comes with a return target that he just take off from somewhere else, and then it happens to be just following this kind of a structure. This is very hypothetical and sort of just to illustrate what was happening in that case. So nevertheless, so we have a single point that is eliminating the mass, which is not too much. All right, so we are just yeah.
So the formula that gamma is following looks like this is without loss of generality.
Say again, Bob, I didn't hear.
It looks as if this is without loss of generality, just taking any gamma, you could decompose it that way. Is that right?
It can, but that wouldn't impose this constraint. That wouldn't impose it to be non-zero. Yeah,
Okay.
yeah, and then you wouldn't be able to put some meaning to the risk-free return if you do that, because so this part will be just contaminated by other parts where beta has a part that is not orthogonal to 1, right? It will contribute there. And then any other residual part will have some part that is not orthogonal to 1, it will contribute there. So it will not be the risk-free return. Yeah. Okay. All right. So and then here is the numerical experiment setup. How do I do with the time, by the way?
11:46, and the seminar goes as you like, 45 minutes.
Oh,
But
that's
you're
nice. That's nice.
Welcome to the time, and by no means obligated to use it.
Yeah, that's nice. Okay, so I have a few other things to say, so I will just explain a numerical setup and then illustrate the performance of maps with the multiple constraints optimization. I mean, this numerical setup is not so broad. This is still a work in progress, as I mentioned, but it is at least looking at some cases where the maps estimator is just showing its performance. Okay, so we are setting an expected return vector as gamma equals r radical p f over the norm. This is a expected return vector as a constraint, and the quantity r squared, if you do the calculation, is standing for the average of the squared returns. If you do the calculation, take the norm and divide by norm squared divided by p will give you r squared. And f is a vector that is really composed of the vector of all ones normalized and the part of b that is orthogonal to z, and then another vector that is orthogonal to both. This is a complete composition, really. This doesn't carry any information about the structure of the returns. This is the numerical setup, really. So we don't claim that A1 is standing for the risk-free rate. This is really the decomposition as opposed to that theorem. Okay, so A1, A2, A3 are sampled uniformly from 1 half to 1. The reason I picked 1 half as opposed to 0 is I just wanted all of the possibilities to show itself without dominating each other. So, okay. And we are setting C1 equals to fully elastic constraint, C2 equals to gamma over the risk return target. Then we are simulating the return model for n equals 50 observations and p equals 500 assets. Okay, what we will do is we will just do the simulation for different return targets that will be units of little r. And we will just calculate the variance forecast ratios. Okay. All right. In this slide, we have return targets set to r over 2, r, 3 over r over 2, and 2r. Remember, r was the average of the squared returns. Okay, so if your average of squared returns is r, then you set your return target to r over 2. You have here, and if you set your return target to r, you have more variance forecast ratio, as you see. If you just aim for more. The variance forecast ratio is growing as you increase the return target. If you aim for more, you will get more volatility, which is expected. And then, and as you see, MAPS method, GPS method is doing better than the PC because it's just killing one optimization bias associated with the first constraint. MAPS is doing better because it's just killing both. And so if you look at R equals R over 2, this is the poorest performance of MAPS compared to the others, I think. It's very close to the GPS. And I'll just take another slide and look at what will happen if I just grow P a little bit more. We'll see this difference. So in this one, so what's happening here is since PCA does not fix any of the optimization biases, because of that P in front of that optimization bias mass in the variance forecast ratio equation that I showed earlier, this starts to grow, this starts to shoot to infinity. Okay, this grows with P. And similarly, remember GPS was like close to like 2.5 basis points in the variance forecast ratio and start to grow, right? So it started to go upwards because it didn't kill one of the optimization bias terms associated with the other constraint. So it's also shooting to infinity. And if you see MAPS estimator fairly close to what it was before for P equals 500. So that is, and the gap between the MAPS and the GPS is just getting larger as P goes different. That's what I'm seeing from the simulation and just supporting what we have in the equations as well. Okay. I think that is the end of the numerical experiment, and I have few open problems. And so one thing open is we have to finish this work. So this is a work in progress, and we like to expand the analysis to k is bigger than 2, especially when we have the possibility of the optimization bias mass canceling each other. So how will that happen, and how to actually come up with an estimator that is suited to that. Because if that happens, and if you use an estimator that only targets one constraint, then that will actually end up in a bad way. So I extend this work with the ongoing efforts of the multi-factor model shrinkage. This is the ultimate project that is in my mind. So you consider a multiple factor model structure, and you consider that means you're considering like more than one B to estimate and more than one constraint to actually optimize the portfolio. So I like to merge these two fields together and extend the work. That is what is in my mind, and I'm free to questions if you have any questions. Yes, please.
I have a question connecting these two. Lots of cases, constraint put on an optimization might also be a factor in your multi-factor model.
Yes.
For example, value was discovered in your second point, or is the optimization bias going to change when the same direction is in both places?
Yeah. So, yeah, this is what I wanted to what I intended to say. Yeah. So multiple factor shrinkage, you're looking at more than one, right? B1, B2, Bk, and that each constraint you add will introduce biases to the estimators of B1, B2, Bk. So one constraint, K biases. So
Yes,
So,
but what
and
happens?
two
when-
constraint, 2K bias.
What happens when a factor in your return generating model is also a constraint?
You mean the,
So I
you mean
might say-
my setup for K constraint?
Yeah, so I might say that return comes from exposure to the market factor and then exposure to the value factor in the specific part. Say I want my constraint to be the value factor.
Yeah.
So does it matter?
Yeah, I haven't think about this yet. So yeah.
Okay.
Yeah.
Second question for me is what happens if you have an inequality constraint, like for some security you want not to go short.
Yeah, that's a good addition to here. Yeah, that is also a good addition. Yeah, this constraint that we're looking at is not having any inequality for this for the scope of this work. Yeah.
My questions, are there any questions from the audience, including the Zoom audience? Like in the chat or just maybe turn the microphone on?
Yeah, so this is time. If you have any questions on the Zoom audience as well. If not, so that is all I really want to say. Thank you for listening.
Thank you. It's really wonderful and
Yep.
Next week we will be again hybrid, I think. Roger Stein will be visiting us from New York, but we'll be presenting here in Berkeley, and hopefully we'll be able to broadcast everywhere as well as just very good. So I look forward to seeing you next week, and thanks again for the thank you for saying and
Thank you. Thank you.